So let's now see the second application of numerical methods which we have in the syllabus. Basically the numerical integration, let's first see, and then we'll go to solving differential equations. So numerical integration. Well, what is the idea? Now sometimes when you are integrating something like this, f of x dx, and you want to integrate this between the limits. Say this I want to evaluate. Now sometimes it may so happen that f of x you don't know the complete analytical form. Okay, you know the values, or it's you know some tabulated values at certain points of x, you know the values of the integrand f of x. So in that case you can't just, because f of x complete analytical expression is not known, so you can't evaluate it by analytical methods, so you have to just then resort to numerical methods is the only way. And sometimes even if you have the analytical form, the expression might be so complicated that the integration method may not exist. I mean, some complicated integrals may so happen that integration is very difficult. The definite integral, I mean, it's very difficult to evaluate integral. So in that case also you have to resort to numerical methods. So basically numerical integration is the process of evaluating definite integral from a set of tabulated values of the integrand f of x. So that is called numerical integration. Okay, and the basic idea is that so basic applications so basic application is that when f of x is not known, and basic application is one when f of x is not known, only the tabulated values is known, some tabulated data is known. Say from experiment you have obtained only the uh, data at some points, so in that case. And the other when actual integration is quite complicated, actual integration complicated by analytical methods is quite complicated. So in these two cases you will be basically applying the numerical integration techniques. So there are three techniques here: the trapezoidal rule, which is quite simple and popular, and then you have the Simpson 1/3 rule, and then you have Simpson 1/8 rule. Okay, so we'll see all this step by step. Okay, so first to begin with the trapezoidal rule. Okay, now to begin with the trapezoidal rule. So what it says is that, let me explain you graphically. So say if you have a curve, okay, between the limits it's not, and so you basically you have, say you want to evaluate the integral between x naught and x naught plus nh. Okay, so I mean this is basically a and this is b, you can say in something like that. So what you're doing is you're dividing the interval, divide the interval ab into n subintervals of width, each interval is of width h. So what will happen is x naught is a, and x1 is x naught plus h, h2 is x naught plus 2h, so equal intervals, and finally b is x naught plus nh. Okay, so that is your xn, in fact xn, which is your b naught plus xn. So this is how it is divided. Okay, let this be y, this will be x. So y is your f of x, right? Y is your f of x. So what this method says is that, so corresponding to h naught, say I have a point here, this is y naught, and this is time being, let's call this as y1, and this as y2, so on, and this is x1, this is x2, so on till x1. So this trapezoidal method, the idea is very simple. What it says is taking the curve in each interval x0 y0 to x1 y1 is first interval, then x1 y1 to h2 y2, and so on, taking them to be a straight line. Okay, so between in each sub interval, if you assume that the curve is a straight line, okay, and here also if you assume that it's a straight line, so now we can just, now basically once you assume it a straight line, the area under this is basically a trapezoid. So area under this basically becomes a trapezoid. Okay, and this area, not this completely. So this area basically becomes a trapezoid. Okay, and now you can basically add. So each of the subinterval become the area in each of the subinterval becomes a trapezoid. Interval is basically is area of trapezium. Okay, that is the idea. So basically you are replacing a curve with a straight line, and so the area under the curve becomes area under the trapezium in that subinterval. So let's now keep it, let's not put this whatever we discussed in maths form. So it's not, so it's not plus h, that is first subinterval, f of x dx will be area of trapezium, and area of trapezium is basically half the mean height, that is y0 plus y1, into the width, which is h here, that is the area of trapezium. Similarly, between x0 plus h2, x0 plus 2h, f of x dx is again half the mean height into the width h. So similarly, if you proceed in this similar way, we can, we can write the x0 plus nh. So all this if you add together, all this if you proceed and add, so what you will get is x0 f of x dx to basically half y0 plus y1 h plus half y1 plus y2 h plus half y2 plus y3 h, so on. Okay, so on. For the nth interval, you will be having half yn minus 1 plus yn into h. So if I remove, if I take common h by 2, I'll get y0 plus 2y1, because you'll have y1 at this, then 2y2, so on, 2yn minus 1 plus yn. So that is the idea. So I can write this in this way. So y0 plus yn separately, and then the terms where the 2 comes. So only at the end points you don't have the coefficient 2, whereas the other you have the coefficient 2. So the area under the curve between x0 and x0 plus nh is approximately equal to, so that's the idea. Basically the area, what we did was simply this thing, area under the curve between x0 and x0 plus nh is approximately equal to sum of areas of the n trapeziums. That's what we did. So it's just simple taking the curve as a straight line and just calculating the approximating the area under the curve in each interval to be area of the trapezium and then summing all the things. So this will be exact. I mean the procedure will be exact if you have more and more points, but and more intervals. So if you take n instead of 6, if you take 12, you'll be approximating the curve well as a straight line. And then because if you reduce the interval, imagine that you are going to infinity, then obviously in very small interval every curve will be sort of a straight line. But if you have n say 3 or 4 or 5, and if you compare that with n being 30 and 40, so obviously when you take larger value of n, you will get a solution which has least error and more accurate. So but then the computational cost also will increase. So that's the idea. So now let's quickly see what is Simpson 1/3 and 3 by 8 rule, and then we'll solve problems all at once. Okay. So Simpson 1/3 rule. So here the idea is basically taking the curve instead of straight line, take the curve as a parabola. That's the idea. So taking curve through x0 y0 x1 y1 and h2 y2. So basically in order to form a parabola you need, in order to form a straight line you need 2 points. In order to form a parabola you need 3 points. So basically take 3 points, basically as two intervals. So these 3 points you try to form a parabola that is polynomial of second order, so that differences of order higher than second second vanish. So that's the idea. Hence we get, so we can just approximate the parabola and we can just write down. So this basically comes from the Newton interpolation formula. I mean in order to derive this you can just use interpolation formula. So we'll not go much into that. We want a final expression f of x dx. So this comes because we are approximating it with a parabola. So this comes from the forward difference formula. Okay, and so del square like del y naught is basically y1 minus y naught. So similarly in that sense you can just, you have to go back and look at the Newton forward formula. So this finally comes out to be like this: h by 3 y naught plus 4 y1 plus y2. So that is what when you integrate it in the two intervals. So similarly h naught plus 2h, so h naught plus 4h f of x dx will be basically h by 3 y2 plus 4y3 plus y4. So similarly you have to do. Now one thing you can notice here is that n has to be even because you are taking two to some intervals at a time. So it's n has to be a multiple of 2, n has to be an even. Okay, that is what one observes. So if you add all this, so let's do it. So if you add all the similar terms, so what you will get is x naught to x naught plus nh f of x dx will be basically h by 3 y naught plus yn, or let me write in this way, square bracket, y naught plus yn, and then 4 times the y1 y3 plus so on till yn minus 1, and 2 times the even terms. Okay, so this is how it is written. So 1/3 rule basically means that given interval must be divided into, so that is, this is the general expression. Okay, so the given interval must be divided into even number of equal subintervals. Well, if it is not equal, and if it is not even, this will not work, since we find area of two strips at a time, right? So that's the idea why we have to define it into equal. I mean, that's the point, we have to divide into even number, because two strips at a time we are taking and assuming that the area, that the curve is like a parabola, and then using Newton forward interpolation formula, and then laying down the area under that root. So that's the idea. Okay. So this is somewhat exact when compared to trapezoidal rule. Trapezoidal rule was quite simple, but accuracy point it lacks, or it requires more and more number of points. But for the same number of points, say if I take n is equal to 10 in the trapezoidal rule and n is equal to 10 in the Simpson rule, and for the same problem if I try, Simpson rule is exact. It's not exact. I mean, it's better in terms of accuracy when compared to trapezoidal rule. So this is all about one third rule. Why this is called one third? Because the okay. So now Simpson 3/8 rule. Okay. Well, this is just an extension of one third rule. So instead of taking n is equal to 2 and 2 strips at a time and forming a parabola, we'll now take 3 strips at a time and form a polynomial of order 3. So taking n is equal to taking the curve through the point xi to curve through points xi, yi, and I varies from 0, 1, 2, 3. It's a polynomial of order 3, polynomial of order 3, third order basically. So that's what. So now same thing, h naught plus 3h here, that is in the first three intervals, and this is again given by Newton forward formula. So Newton forward interpolation formula, basically, like if you want to approximate a polynomial with third order, then you'll have an expression for that, and based on that you can just evaluate the area under. So this comes 3h by 8 y0 plus 3y1 plus 3y2 plus y3. So this is for the first interval. Similarly, if you can write it for h0 plus 3h, no, h0 plus 6h, f of h dx will be basically 3h by 8 y3, and then y4 y3 y4 plus 3y5 plus y6, and so on and so on. So you have to just proceed in the same way and so on. So if now you add all this in order to get the total area, you have to add all that. So adding all such intervals, so it should be h0 to h0 plus nh, f of x dx will be basically 3h by 8 y0 plus yn, let me put a square bracket, y0 plus yn plus 3 times y1 y2 y4 y5 plus y7, so on, plus 2 times the y3's and multiple of 3 terms. Okay, so that's the idea. And this can be anything. So 3 times the terms, just accept the third and the multiple of third terms, and 2 times the multiple of 2 times the third, I mean the y3's and y6 and y9's, the multiples of 3 terms. So this is called 3/8 rule, and this obviously increases the accuracy because you are approximating, taking 3 strips at a time and approximating it with the polynomial of third order. But remember, then n has to be a multiple of 3, so you can't choose n to be something arbitrary, n has to be a multiple of 3. Okay, so that is one of the restriction that this method lays out. So we have seen trapezoidal rule, we have seen Simpson one third rule, and 3h by 8 rule. So this is just a simple way, and approximating a definite integral with series of just additions. That's the idea. Okay, which a computer can do. A computer can do addition and subtraction. It cannot do multiplication division. Basically, it approximates multiplication division to be addition and subtraction. So this thing, an integration, you can just automate this process. You have to just feed in this formula. In the case of Simpson 3 by h, you have to just feed in this formula to a computer, and then it will just approximately calculate it. Now you can increase the multiples also, so it will take less time. So this is how numerical methods have evolved, have an advantage when it comes to automation and when it comes to computation through a device rather than manually. Let's now solve one problem which describes all these methods. So evaluate g in the interval 0 to 6 1 by 1 plus h square by using one the trapezoidal rule. The second is Simpson 1/3, and the third is Simpson 1/8, or 3 by 8. Sorry, this is 3 by 8. Okay, 3 by 8. So that is 1/3 and 3 by 8 rule. Okay, so we'll try to solve it using this. So now let's take 6 intervals, because because we can apply 1/3 rule because it's a multiple of 2, and a 3 by 8 rule because it has to be a multiple of 3. So and trapezoidal rule, there is no such restriction, so you can use six sub intervals. So let's divide the interval 0 to 6 into 6 parts, each of width h is equal to 1. Okay, and the values are given below. So you have x here. Let's form a table x and f of x. Okay, so x is 0, then 1, then 2, then 3, then 4, then 5, and then 6. Okay, so now okay, so this is at 0. You have to just know f of x is basically your 1 by 1 plus x square. So you have to just substitute x0. So when you substitute x0, it becomes 1. When you substitute x equal to 1, it becomes 0.5. So just computing the values. When you substitute 2, it becomes 0.2. When you substitute 1, it becomes 0.3. When you substitute 4, it becomes 0.0588. So because the function is given, you can just easily evaluate these values. So this becomes basically y0, this is y1, this is y2, this is y3, this is y4, this is y5, and this is y6. So you have all the points. Now once we have the tabulated data, now we can apply each of the rule. We know the final expression. So trapezoidal rule, what it says is 0 to 6 dx by 1 plus h square has to be h by 2, and then just the endpoint summation plus 2 times the remaining points. Okay, so that is the idea. So you have to just h is 1 here, width is 1 because 6 you have divided in different way, so h is 1, and then you have to just add the first and the last point and twice the remaining points. 8, 5. So this is how divided. So now when you add this together, you're using a calculator, this comes out to be 1.4108. This is by trapezoidal rule. Now let's apply Simpson 1/3 rule. Okay, let's now apply Simpson one-third rule. So let's see now one-third rule. So Simpson one-third rule, what changes is only the formula. So it's h by 3, the end points y0 to y6 plus 4 times you have the the odd terms and 2 times the even terms. Okay, that is the idea. 4 times the odd terms and 2 times the even terms. Okay, so 1 by 3, which is 1 plus 0.027 plus 4 times the odd terms, 5 plus 2 times the even terms. So this, when we evaluate using a calculator, this comes out to be 1.3662. Okay, this comes out to 1.3662. Okay, so now let's see Simpson 1/8 rule. Okay, so when I applied through Simpson 1/8 rule, so this was 1/3 rule. Okay, so sorry, 3/8 rule. So because this is, you will get 3h by 8 in the formula, so that's why it's called 3/8 rule. So this, let's see how to apply this Simpson 1/8 3 by 8 rule. Okay, so Simpson 3/8 rule. So basically comes in this form. You have 3h by 8, and then you have the initial and the end terms, then 3 times the terms just excluding the multiple of 3 terms, and 2 times the multiple of 3 terms. There is no y6 because y6 is at the end, so it goes the end into the first term, and there is no other root. So this is what the complete expression looks like. So we just substitute h as 1. So y0 is 1 plus 0.027 plus 3 times 0.5. Let's just, I'm substituting the values. 385 plus 2 times 0.1. So this, when you solve, it comes out to be 1.3571. So now we have evaluated by trapezoidal rule, we have evaluated by one-third rule, and we have evaluated by Simpson 3/8 rule. So this is how a simple problem, I mean, just it's quite simple, I mean, to apply these methods. So mostly the Simpson rule is used, okay, I mean, you can use trapezoidal also, depends on your thing, your convenience. Okay, so now let's solve another problem. The velocity in kilometers per minute of a velocity of a mopped which starts from rest is given at a fixed interval of time, is given at a fixed intervals of time, which is in minutes, as follows. So 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 experimentally observed data is given. Okay, t and v experimentally it is given. Okay, so t is 2, then 4, then it takes 6, then 8, then 10, then 12, 14, 16, 18, and 20. Okay, and the velocities are 10, 18, 25, 29, 32, 20, 11, 5, 2, and then becoming 0. So it's getting stopped at it. So now what he wants is estimate approximately the distance covered in 20 minutes. So that is what is asked. Distance covered in 20 minutes. Okay. So now S is, let the S be distance, and which we are calling in kilometers. So I can write ds by dt as v. Okay, that is the general. I mean, the derivative of distance just gives you the velocity, derivative of displacement, and it is moving a straight line, so has to be displacement and distance are same, so when it is moving a straight line. So ds is v dt, and s from t0 to t is equal to 20 is basically integral v dt 0 to 20. So this basically becomes evaluation of definite integral. Okay, so let me write down clearly here. S is equal to v dt 0 to 20. Okay, so this integral we have to evaluate, and we'll use Simpson 1/3 rule. I mean, unless otherwise specified, in the exam they will be specifying, but unless otherwise specified, you can use interval. So now here h is basically h is 2 here, because that's how between 2 to 20 you want to evaluate. Okay, starting from rest he has given, so time is 0, velocity is also 0. This is the point which is given starting from rest. So h is 2, equal shaped interval, h is 2. Okay, and v naught is 0 at the start, and v1 is 10. So these are all v1, t1 and v1, t1 and v1, t0 and v0 is 0. Okay, so now this integral basically 0 to 20 v dt becomes h by 3 plus the n terms plus 4 times the odd terms plus 2 times the even term. Okay, so we can just substitute it. Okay, where x term is the v0 plus the last term, that is v10, so this is 1 and this is 10th term, plus 4 times the odd terms, that is v1 plus v3 plus v5 plus v7 plus v9, plus 2 times the even term, which is v2 plus v4 plus v6 plus v8 term. Okay, so you just add this, h is 2, so it is 2 by 3, v0 is 0 plus v10 is 0, because at the end velocity come to 0, plus 4 times your initial terms, that is 18 plus 29, sorry, this is even odd terms, so 10 plus v3 is 25 plus 32 plus 11 plus 2. Okay, plus 2 times v2 is 18 plus 29 plus 20 plus 5, so this is v2. Okay, so if we just evaluate this comes out to be 309.33 kilometers roughly. So this is the distance which it travels. So now here you don't know whether velocity is increasing or decreasing, what is happening in between, you don't know. So I mean, if you happen to solve it by trapezoidal loop, you will imagine that that velocity steadily increases in the interval, but this is 1/3 Simpson rule. Okay, so that's how. So sometimes this is one of the application where you don't know how on what forms velocity it is. So this is the best approximation you are doing it for the distance by Simpson rule. So distance traveled is basically 309.33. All the three, I mean, all the three methods we have derived it for trapezoidal method, and Simpson 1/3 and 1/8 comes from Newton's forward difference formula. So based on that we have derived all that, and then we have solved two examples. One was showing all the three methods, and the other was a physical problem basically. How do you apply that to an experiment? So this was physical, means you have a data which is obtained from observation or from experiments, and then you are calculating the distance. So the basic idea is bring in the mathematical integral form and any definite integral, you can just evaluate it with the help of just tabulated data. Means if you know the function values at some intervals, then you can just evaluate the data. So that's the idea.